let's make sense of the bond energies then. Okay. Look at a CC single bond. Look at the bond energy, 347. Now look at the double bond. You would think that a carbon-carbon double bond would be exactly double that of a single bond. You would think. So if I multiply this by 2, 347 times 2 gives what? Gives me 694. Yeah, 694. But it's only 611. And the reason why is because this second bond being formed is a pi bond and not a sigma bond. Okay, and so, you know, the sigma bond, the initial single bond, is always going to be a sigma bond, and that's always the strongest bond that's formed. And if you start forming p orbitals overlapping on top of that, the pi bonds, because it's weaker overlap, it doesn't quite double the bond energy from a single. Okay, so that overlap concept is actually pretty key to understanding bond energy. And then you look at the triple. You would think the triple would be 3 times the sigma. So what's 3 times 347? 994 plus 47. I can't do math in my head right now. What's 94 plus 47?
1,041.
So yeah, okay, 1,041, thank you. Yeah, so 1,000 calculators to rescue, right? So 1,041, okay, you would think this would be 1,041, but it's only 837, right? So adding a second pi bond doesn't exactly add double the energy of sigma, right? And again, it's because of the weak overlap of 2 p orbitals trying to overlap. That's weak. That's weaker. Okay. So it gets back to this concept. The initial sigma bond is the single bond. Okay, so what this is here's your bond in the middle between the 2 atoms, and then your pi's are outside. Okay, but these 2 pi's are weaker. So put a star on this slide and memorize it. Single bonds contain 1 sigma bond and 0 pi bonds. You'll have to write that in. Okay, so a sigma bond and 0 pi bonds. That's just any bond. Any single bond has just 1 sigma and 0 pi's. Okay, if you have a double bond, it'll contain 1 sigma and 1 pi bond. And if you have a triple bond, you have 1 sigma bond and 2 pi bonds. Okay, and the sigma bonds are always made using hybridized orbitals. The pi bonds are always made using unhybridized p orbitals. For the sake of simplicity, we're doing that. Okay. So you'll always get these weird lobes in the lobe pictures from your chart. All right, you'll use those to determine how many sigma bonds you have. But then the pi's are added to those. Bear with me here. It'll come together, I promise. Oh. So basically it's 1, 1, 1, and then 0, 1, 2.
Pi bonds are weaker than sigma bonds. Why is it that like carbon dioxide with the double bond is super easy, or sigma bonds are very hard?
Well, yeah, I mean, a double bond is still pretty strong because it's got that extra. Okay, so I think what you're asking. So you're saying, well, if carbon dioxide has double bonds, why is it strong to break apart when you're telling me that pi bonds are weaker? Well, in carbon dioxide, you've got a double bond, you've got a sigma bond, and then you also have a pi bond. So breaking a sigma bond and also a pi bond is more difficult than to break only a sigma bond by itself. So it's not either or. All right, the bonds in carbon dioxide have a sigma and a pi bond together, which makes them strong. Okay, it's just that every time, okay, well, here's another comment I'll make. You cannot have pi bonds unless you've already made a sigma bond first. Right? The initial bond that's made between atoms is always going to be a sigma bond first. Okay, the pi bonds come after. All right, so the pi bonds are only additive to what the sigma bonds have. I don't know if that clarifies anything or not, but okay. So let's do some examples, okay, of double and triples. All right. So we did all single bonds with methane. We did that. All right. Those were all sigma bonds, right? So methane, CH4 bonds. There's 4 of them. They're all single bonds. They're all sigma bonds. Okay. Now we'll do formaldehyde. Formaldehyde has a sigma bond here, a sigma bond there. One of these two is a sigma bond, and the other one is going to be a pi bond. So if we hybridize that carbon to account for that, okay, it's a steric number. What is the steric number of this carbon in this structure? Steric number is 3 bonded atoms, 0 lone pairs on the carbon. This is steric number of 3, right? 3 bonded atoms, no lone pairs. What is the shape going to be? It's going to be a trigonal plane. Can we draw a bonding model to illustrate that shape? Okay, well, to do that, if we're going to make 3 bonded atoms and hence make 3 sigma bonds to do it, we have to hybridize 3 out of these 4 electrons to make these 3 bonds. So I'm grabbing 3 out of this bunch and I'm making 3 hybridized orbitals with those. There's going to be 1 left over from here, and this will be used to make the pi bond with oxygen. So carbon, unhybridized again, 2s2, 2p2, 2p2. We take 3 out of there, make them all the same so that they can bond according to the trigonal plane shape, and then this 1 extra electron is left over for a pi bond. Yes?
I think for the trigonal plane.
So steric number, 1, 2, 3 bonded atoms, 0 lone pairs. Look at your chart. It says steric number 3, trigonal plane. Trigonal plane is also the electron and molecular shape in this case. Let's draw a valence bond sketch for CH2O. All right, so so we'll take carbon. What is the valence bond sketch of this? Oh wait, I left my chart somewhere else. I can bring mine up here. Actually, I got it here. All right, so it's okay. Keep yours. Yeah, good. Okay, so we look at CH3. We look at CH2O. We determine it's going to be this shape, right? It's going to be carbon, double bonded to oxygen up here, and single bonded to these hydrogens down here. So the picture is going to look like this for our sigma bonding framework. So I'm going to do that. Let's make some loads. All right, so there's my trigonal plane. Okay, and then my hydrogens are down here, and they're just going to bond with their 1s. My oxygen is also outer. It will bond with one of its 2p electrons. So why do I have circles here, but for the oxygen I got 2 lobes? Why is that? So these 2 lobes together make up the unhybridized hybridized 2p orbital, okay, for oxygen. So these are not hybrid orbitals, okay? It's just two lobes of an atomic p orbital. So for oxygen, it's not inner, so we don't hybridize the atoms, or we don't hybridize the orbital. Okay, we just say, okay, oxygen, the highest electron in oxygen is a 2p. Okay. What are these described as? Okay, these are described as sp2 hybrids. Okay, so this is a sp2, this is an sp2 hybrid, and this is also an sp2 hybrid. So this bond right here, that bond, this is what we call a sigma, and we say it's overlapped, or it's made by overlapping an sp2 with a 2p. This is also a sigma bond with the hydrogen. We say that that's made by overlapping the sp2 carbon with a 1s of hydrogen. This is also a sigma bond sp2 with a 1s. So in this molecule there are 3 sigma bonds because the carbon is bonding to 3 atoms. Get this out of the picture here. But we need to deal with the double bond still. What do we do with the double bond? Alright, so I'm gonna draw the same picture again over here. Uncluttered with all the labeling. Okay, now if I want to add a pi bond to this, okay, because every time you have a double bond, remember you have 1 sigma and then 1 pi. Okay, so here are my sigma bonds. But if I want to add a pi, now I'm going to take 2p orbitals and overlap them. Now, if I had, really nice graphic software, I could combine these lobes together. But because I have to somehow fit in the sigma inside here, this is the best I can do. Now this looks really strange. It looks like I've got 2 bonds here, right? But the really hard thing to understand first, but you'll get this, is that if I took this out, it's really this. It's just 2 p's it's really this. But I can't fit all this inside here. Okay, so I have to spread it out and just draw 2 lines to try and depict these 2 connection points here. And that's the best I can do by hand. Okay, so looking at this picture, I got 3 lobes. That's this part. 3 lobes. But then the pi bonds are added in addition to this basic picture. Okay. So I have to add the pi bonds on top of that. Let's count the valence electrons in carbon, okay, just to try and connect the dots here. I have this arrow here, I have this arrow here, and I have this arrow here. So here are my 3 hybridized electrons in carbon. And then I have just the 1 unhybridized electron. But remember, it occupies, this is like a px orbital. Alright, the electron gets to occupy that by itself. So it's 1, 2, 3, 4 valence electrons for carbon bonding in this model. But only one of them is being bonded in a non-hybridized p orbital. Okay. So that 1 in the p orbital, right, this 1 arrow here is this 1 arrow here. These 3 arrows here that are now being hybridized into new hybrids, those are these 3 arrows here. And your head's probably like ready to explode right now. Okay. Okay. If you're going to go on into OCHEM, you're going to need to know this. Okay. And I teach as if you're going into OCHEM, okay? So if you don't know what sp3 hybridization means in OCHEM, like if you walk into that class and you don't know what that means, your instructor's going to get very upset with you. And then they're going to ask you, who did you have for Chem 111A? And you're going to say, yeah, I had Fernandez for Chem 111A. And they're going to say, he didn't teach you about hybridization? You know, so I'm going to look bad if you don't know this. So I'm making it a point that you know this, okay? The way that they describe bonding, especially when you get to OCHEM, we describe bond strengths and as a result the amount of acidity a compound might have in a solution by how much it's willing to give up a proton. Well, the bond strength of giving up a proton has to do with how much or what kind of hybridization you have in the bond. Okay. The more S character you have in a bond, the stronger the bond is going to be, because the electrons are closer to the nuclei in those bonds. Okay, so sp hybridized atoms tend to give stronger bonds than those that are sp3 hybridized, for example. All right. You'll get into that when you get to OCHEM. I'm just kind of throwing it out there to plant a seed that maybe might sprout a year from now. Okay. Okay. This is beyond chapter 6 and 7. This is probably the most difficult concept to understand. Okay. You know, what is hybridization? Okay. Now, in terms of just applying it, okay, let's just do one more here with the triple bond, and then we'll take a break. Okay, I got to cover this, and we're going to do the lab packet today. So here's again, carbon is unhybridized. Notice how every time we're starting from an unhybridized starting point. Now we're going to do it for hydrocyanic acid. Okay, here's your nomenclature, going way back to that. How many, what kind of bond is this going to be again? It's going to be a sigma, because all initial single bonds start with a sigma. They start with hybridization, okay? What about this center bond right here? That's also going to be sigma. And then what about these two?
2 pi bonds.
That's going to be 2 pi bonds, okay? So we're going to hybridize carbon such that it is now going to be sp hybridized. Okay, why is it sp? Well, we have to go back to, again, our chart. So HCN, it had a single and a triple, 2 bonded atoms, no lone pairs. Steric number 2, it's going to be a linear compound. The carbon will be in the center with 2 lobes on it for the initial bond it's going to make. So here's your HCN. We're only bonding to 2 atoms now, so now we only need to hybridize 2 of the electrons from the initial 4. These other 2 are going to be used to make each of one of these pi bonds. So this arrow might be used to make this bond, and it'll spin pair up with an electron from nitrogen over here. And then this other arrow here will be one of these dots that was in here, and it will spin pair with one of the dots from the nitrogen. All right, just to relate it a little bit back to Lewis structure, or Lewis theory. So, going back to Lewis structures again, it's just, here's a dot, and here's a dot. Those would be these 2 dots here. And then these 2 dots would be these 2 dots, right here. But again, it's like, what are the orbitals that are being occupied there? Right? Let's draw a Vesper sketch for that. Okay, so for HCN, all right, so here's the Lewis structure. Here is the Vesper sketch. All right, what bonding takes into account that shape? Okay. Here's the VB sketch. How do I start? Look at your chart. How many lobes do I put on that carbon?
2.
I put 2. So I'm going to start by putting carbon in the center with 2 lobes. Hydrogen bonds with which orbital? Hydrogen always bonds with this 1s, right? So I'm going to make a sphere where it's hydrogen there. Nitrogen, what orbital is most likely nitrogen going to bind with? What's the highest energy orbital that's usually occupied by nitrogen? It's 2p, right? So we're going to go ahead and draw nitrogen with its 2p here. And that is the sigma framework for this compound. So I'm going to write here, zoom out a bit here. So this is sigma bonds only. But to complete the picture, now I'm going to add 2 pi bonds. So maybe nitrogen has its 2px being used here. What about the 2py? And also, what about the 2pz? So I'm just going to label these.
Can you just re-explain the process? The adding of the...
So we're okay with this?
Yes, just whatever you just did.
Right, so just to do that, right, so we'll call this the 2px of nitrogen. We'll call this the 2py of nitrogen. We'll call this the 2pz of nitrogen. So the outer atoms don't need to use hybridized orbitals to bond, because they are not central atoms. So with nitrogen, it has 5 valence electrons. We can just say that it's going to use 2p to bond. Okay, here's also maybe a 2pz and a 2py on the carbon. Okay, so this is going to be a 2pz, and this is also going to be a 2py. Okay, but these in here, this is an sp. Okay, so we're gonna connect these now. Okay, so here's trying to do some three-dimensional structure here. That's one pi bond, and here is the other pi bond. Notice how I have this line going behind this one, okay? And that would be the triple bond. So let's redraw this now without all this stuff, without these labels. So, starting from the beginning, triple bond, 2 pi's, 1 sigma. 2 pi's, 1 sigma. Right? Here's my outer bond. Here's my inner pi bond. Why do I say inner? It's actually, both the pi bonds are perpendicular to the bond axis. So these two lines here represent only one of those lines in the Lewis structure. Because, remember, it's 2p orbitals overlapping to form one bond. But they overlap at 2 points, at 2 connections. Okay. Here's another line. These two lines represent the other line in that Lewis structure. And then the middle line in that triple bond is just this right here. It's the hot dog and the bun. Okay? Here's the hot dog inside the bun, but the bun requires 4 connection points for a triple bond. Sorry for the analogy, but it kind of matches, right? It's a hot dog and you get all buns, right? So the hot dog would represent the sigma bond in that analogy, right? So hopefully you're able to at least draw this verbatim for what I have here. Okay. Try drawing this one on your own. Let's just try it. Okay. I want you to try it for this one.